In this video, we show the practices that support ongoing changes in student thinking. We'll feature sense-making. Students will be given opportunities to reason, to compare emerging science ideas with everyday experiences outside the classroom, or science ideas from their past. They'll be asked to use evidence to support claims and then revise their thinking. None of this sense-making can happen without structure and support by the teacher. We'll see how the teacher scaffolds all of this work with tools, routines, and talk.
So Casey asked this question the other day. She went to Starbucks. This is real. This is not made up. She went to Starbucks. She got an iced drink because she's lucky. Okay. She set it down on the table, and a few minutes later, she realized that the outside of the cup had water on it, and that there was a puddle forming on the table. Okay. So her question was, where'd that water come from, and how'd it get there? So what is that little puddle that forms? So this is like the best example of an idea question that I can give you. Something that your classmate asked that we want to just share our ideas about. Then we're going to learn some stuff, and we're going to come back to this question and see if we figured it out or not.
I don't know.
Zelda, where do you think the water came from?
It had a hole.
It had a hole?
No.
So from inside?
Yeah, from the inside.
Yeah, but how did it get out?
Condensation.
Condensation. What is condensation? What is condensation?
Yeah, it's like
You have like icing a cup or something? Like a little something.
Why?
I thought condensation was rain.
I don't understand how we got wet.
The water. So where do you think the water come from?
Yeah, that's exactly.
You know.
I don't think they
Every cup has a hole. Are you drinking? Yeah, but other cups do that too.
not all.
Like the ice, from the ice. It's like they put it in, and then there's like little drops coming like through the from the cup, and then when you set it down on a table, the drops keep coming and they form a puddle.
Right. So the water come from the ice?
Yeah.
Ice inside of the cup?
Or it could come from the water from the water, like you know how they get the water.
Is the drink cold or is it hot, like in the room, or? Because the drink is cold, right? So you're saying because the drink is cold and the temperature in the room is much different and it's warm. That makes it do that. The temperature of the drink, cold, and the temperature of the air in the room, warm, and that has something to do with it. That's a great start. Wes, what did you write?
It was cold on the outside and it started to melt like ice.
Okay, so the ice that is inside the drink is actually melting and moving outside of the cup? Okay, any ideas, Victor? Any ideas about how that ice can melt and move outside of the cup?
Because the sun is like hitting it, even though like it's like something that you can't see through. It's like heating the cup, and like the cup is heating the water kind of.
Okay.
And then it boils kind of. And like it grows from like outside of that, and you see water, and then yeah.
So the water molecules from the ice are actually moving through the plastic of the cup.
I swear.
Okay. So are you kind of agreeing with what Victor and Bless are saying, that the molecules from the ice are leaving the cup? They're like melting through the cup, kind of, is what they said? Not really. So you have a different idea, and it's about forcing. So can you explain a little bit more about that? It sounds like you're saying that the ice. That the ice in the drink is actually making the air in the room colder. Is that what you said?
I was making the cup colder.
The cup colder. Ah, okay. And then what does that do?
It makes it form.
we want to answer Casey's question. So what we're going to do is step by step set up a lab today and collect data. We're going to do this a little bit differently than normal. So we're going to do this backwards today. We're going to set up the experiment and talk about what we think is happening and get our data and try to make a conclusion about it. And then tomorrow we're going to fill out the experiment paper. The reason for this is that my other classes, when they're trying to fill out the experiment paper, it's been like kind of awful. It's just really hard to think about it before you've done it, and so we're just going to flip it. So everything from here up should be copied into your journal, and then you're drawing molecules both in the water and above the water to show what's happening at the surface of this water. Hint, you might draw more than one type of molecule.
Surface of the water is just water.
There's more to it.
You ladies don't know nothing.
These molecules are getting pushed out by these ones. They're forcing them out. And they're going out here to turn into air molecules.
Turn into the air molecule?
They push them out. And they turn into air molecules.
What do you think? Do you agree?
Yeah, I drew that too.
You drew the same thing?
Well, yeah, I drew that the molecules are pushing them to the surface.
What about at the line? Did you draw anything at the line or above the line?
Yeah,
What did you draw?
I drew molecules on it. So it feels like it's pushing it to the other side.
Oh, so the water molecules below the surface are pushing water molecules out of the liquid. Okay. Did you draw anything else? That's a good description. Okay.
Yes, we're bumping into each other, making other molecules pop out of the liquid.
Okay, so the only extra information I need from you is what type of molecules you're talking about.
Swish. Water molecules.
So the water molecules are below the surface and they're getting bumped out of the water, but they're still water molecules when they're above. They're just alone now.
They become gas molecules.
Okay. Did anybody add anything different to their drawing that you haven't already heard?
Alright, see the little lines, the lines? Like the red line in the circle? Alright, on
This is
bottom
the
of it?
surface of the water.
Alright, yeah, on the bottom, I just circle the molecules with 2 lines to like the temperature. And then on top of it, I put X's as air molecules.
So you drew 2 different types of molecules.
Yeah.
Okay. So are you also showing molecules getting bumped out of the liquid?
Yeah.
And turning into X's.
So are they turning?
Yeah.
So they're turning into X's, or are there water molecules in the air as well?
Well, like there's only a little bit of X's on top and like a lot of like the molecules on bottom, so it could look like, and then like the molecules are kind of facing up, so it looks like they're like moving up.
Okay. Are there any water molecules that are above the surface of the water
3.
in your drawing?
Oh, like, I guess, yeah.
Well, look at your drawing. I'm telling you. But you are now taking one of the tall, narrow cups, and you are covering the water.
No,
Don't show me.
it's different.
Oh, I see.
X's, and circles, like X's as air molecules and a little bit of circles. Like, cause like, yeah, because I circled as water molecules and X's as air molecules.
So you drew a mix of both air and water molecules floating around this gas in there. Okay.
I do the water vibrating to the next cup.
So you drew water molecules up in the top of that cup. So you only drew water molecules. You didn't draw.
No, I do.
Did you draw any other type of molecule?
Yeah.
What kind? Air molecules and water molecules. So that sounds really similar to what Victor did. he drew both air and water molecules up there as well. What is the only way that we can get those water molecules that are floating around just like a gas, like Henry said, how can we get them to come together again and form a liquid? What could we do to make them clump back together and form a liquid? We've got them all separated out, but what could we do to see if they're there and clump them back together? So how do we get the water molecules in a liquid to spread out like that and turn into a gas? What's one way we can do that? So we can heat the water and that will make them spread out. So what might be one way we can get the opposite effect and get them to clump back together again? Make it colder? Tim, what do you think? Does that sound like a good idea? So if we cool the air on the top of the upside down cup, then water, you choose, will or will not form, and try to explain why.
So what do you expect to see?
If we left it out, we'll probably see bubbles around it.
Bubbles?
Yeah, like small water drops.
Small water. Where?
Around inside the cup.
Inside the cup? Because?
I don't know.
You don't know? Where those water come from?
Here, the water
Water.
in the cup.
The water, the bottom of the cup?
Yeah.
How that water get up? You don't know.
If we cool the air on top of the upside down cup, then the water will not form because there is no water like in the inside.
Okay. So my guess is, Alicia, that when you drew this, you only drew air molecules up here, right? Okay, so that's your prediction. Okay, did anyone have a different prediction than Alicia?
Why would someone put ice on the cup, upside down cup, because the ice flows and one molecule attaches to another molecule until it forms water.
Okay, so Tim, I'm guessing that when you drew this up here, you drew a mix of water and air molecules, because you're talking about water molecules. And take a look inside that cup. Do you see water forming, a little bit of fog or something inside that cup?
Yes, I
Go ahead and dry it off, look at it, reach inside, see if you can wipe it away if it's there. This doesn't work either.
So did you see the steam inside of the cup?
This one too.
This one has steam too.
So where does the steam come from?
The coldness of the ice. The molecules
Pass through the cup.
or the cup molecules push the ice water in.
So I saw that most people found they had water on the inside of that cup. So if you don't believe that it's on the inside, reach your pencil or your finger inside and try to wipe it away and see if it really is on the inside. It is. Okay? Then you need to answer this question. When we cooled the air in the cup with an ice cube, water formed because. If your explanation is the same as your prediction, just draw an arrow to your prediction. You don't need to copy the same answer, but see if you can explain what's happening to the molecules, what type of molecules they are, and why they're doing what they're doing. Right now, in this moment, where are you at? You're going to have the chance to change your ideas, so don't worry about being right or wrong. I just want to know where you're at. Your Post-its are not going to be the only ones up there.
Can you do both of those?
Say yes or no. Henry's going to make a guess, and he's going to say inside or outside. No, decide inside or outside. Just make a decision.
Sure.
There's no middle ground here. You have to make a decision based on what your best guess is.
Where does the water on
So yours is going to go there. And I think you put this on the wall. process.
No. Yeah. I have to go do it.
So it looks like our class is pretty split, okay, on this question, whether or not there's water molecules in the air. So I am going to ask for your ideas about question number 1, if I call your name. Okay, so our first person is Milan. Where did you put your Post-it? Yes or no?
Yes.
Okay, can you explain why you think that there are really water molecules floating around in the air? How do you know that?
Because when we did the Starbucks experiment and we checked the inside of the cup to see if it was like wet or something, it was wet. So that told me that there were water molecules in the air.
Okay, so what did you see at the end of that experiment, just to remind people?
That it was probably.
Okay. Milan's just done something pretty awesome, and I don't think she realizes it. Maybe she does. But not only did she give me her reasoning, so she said, well, I wrote yes, and I explained why I think that. She also cited evidence from class, so she told me something that she saw that proved to her that there are water molecules in the air. Okay, that's a really big deal because not everybody is used to using evidence in that way. So when you answer, when we're asking for your stance, for your position on things, I want you to try to do what Milan just did and try to give me evidence. You might not have evidence, but try. So I would like to hear from somebody who put their Post-it on the no side. Because we've heard a lot of arguments for this side, but we haven't heard anything for this side.
I said no because yesterday when we were talking about how water molecules bump and then in the air it turns into gas molecules, so it doesn't stay a water molecule in the air. When it's in the air floating, it turns actually into a gas. And then as also when we had did our one experiment where we had got gas, liquid, and solid molecules, we noticed that gas was in its own category and not in water, well, in water category, so it would have to change. It wouldn't be able to stay the same in the air.
Okay.
Otherwise we would be able to see it, but we don't see it.
Okay. So, Quentin, is your main argument that because you don't see water as a liquid in the air, it must not be there? Is that your main argument?
Yes, this one is.
One of them. So then the other main argument would be this, how we put molecules in different categories. And your argument is that water fits in the liquid one. Okay.
One of them too.
So you're talking about the actual process?
Yes.
Okay. Okay. Anybody else that wants to argue for the no side? Alana?
I said no because if there was water molecules in the air, we would be able to feel water pressure.
Okay, so that's another sense argument. You're saying, well, I don't feel, my face doesn't feel wet, so I don't think there's any water molecules in the air. That's sort of like the part of Quentin's argument where he said, I don't see water in the air, so it must not be there. All right, so Alicia had her hand up next, and I think Henry wanted to share as well.
I said no because water just doesn't float in the air or anything. It turns into a gas.
So is that sounds to me like it's really similar to Quentin's argument. So can you say that one more time, Alicia? And Quentin, I want you to listen really carefully to what she says and think about whether that's the same thing you're saying.
Okay.
Okay?
I said no because that water just doesn't like float in the air. It just turns into a gas.
Does that sound like your argument in one sentence? Okay. All right. And Henry, what did you want to share?
Oh. About the air.
Yeah, where did you put your Post-it?
Like GS.
Okay, and why?
It's because when the room gets, when it gets cold, you can see water in the wall. If it gets cold in the room,
like there's water back to ceiling.
Okay. Have you seen that happen before?
Yeah.
Okay. Say that louder. Say it loud so everyone can hear, especially Henry.
On the windows?
Yeah.
So you've seen that happen on the windows when it's really cold in the room?
Yep.
Outside.
Okay. Okay, so we're going to do a little experiment. We're going to do 2 experiments today, and one of them we're going to set up now because we're going to try and get some evidence that will help us decide what our answer to this question is and give us something to back it up. So up here, I have a jar that is made of glass. I am going to fill my jar with air.
I think I throw that in.
No, why would I throw that? It's full of air now. If we cool this jar down just like we cooled down our air yesterday, we should see water forming inside the jar.
Yep.
Can you check that that's closed nice and tight? Please don't break it. Okay. Okay, so it's closed. It's not going to open. I'm not going to move it. So we're not going to add anything to the inside. If there's no water molecules in the air, then we won't see anything, right? Okay, so I have up here an ice bath. It's super cold water. You can see how cold it is. And I have just something heavy to weigh down the jar so that it stays in the cold water. We're just going to leave it there for most of class, and we're going to check in on it later. So now let's talk about this one. Over here, we have a little bit less division in our class here. Most people are kind of arguing for this side, that the water on the outside of Casey's Starbucks cup is coming from inside of the cup. All right. So, Curtis, can you tell me where you put your Post-it and why?
Outside of the cup.
Okay, so you are in the minority right now. So make a bold argument, sir.
Because there's air, I mean, there's water molecules in the air.
Keep going. So there's water molecules in the air? So how do they get to the side of the cup? Okay. And what makes them get attracted by the water? Okay, anybody else who argued for outside of the cup that has similar thinking to Curtis? Anybody think that he's got some good ideas? So this one says, I think it came from the outside because the ice inside maybe made the air around the bottle or the cup cold enough to make the cup or bottle moist. Here's Curtis's. It says because there's water molecules in the air. Another one that says the ice being inside the cup makes the drink a different temperature than the air. I want to know if that is you. Janet, did you put yours inside? Okay, could you please explain why you think that it's coming from inside the cup?
I think it's like both because it depends how hot the room temperature is and how cold the water is.
Okay, so what would be a situation where the water would come from inside the cup?
When it has ice.
So if the drink has ice in it at all, then the ice will melt outside of the cup? Does that sound like the idea?
I wrote that water came from the inside of the cup.
Because? Well, what made you guess that?
When the ice cube melted inside the cup.
You know how when you said the ice was there, I think that it's from inside the cup because there's when it's cold, there's like yesterday in my house, it was cold outside and then I had steam in the inside of my window.
Okay.
I don't know.
So the difference, so Alicia, you're talking about a difference in temperature. You said it's cold outside, but it's warm in your house, right? And there's steam forming on the inside of your windows. So can you compare that to our cup, to our Starbucks drink? How is that example like our Starbucks drink?
Because there's like water on the outside. Cold steam or whatever.
So is the water or the steam that's forming, is that on the cold side of the cup or the hot side or the warm side? Because in your house you said that the steam is forming on the warm side of the window. Think about our cup. What's inside of it? Is it cold or warm? Cold. And is it cold or warm outside in Starbucks where Casey was sitting? Warm. So the steam is on which side? The cold and warm side? Cold. Cold. So it's cold in Starbucks?
It's like it's on the warm side.
It's on the warm side, right? So we have a little pattern here where we're starting to always talk about steam forming when there's a difference in temperature. There's a warm side and a cold side. Okay? All right. So in your lab kits today, you have a jar. You have a jar that has not jelly or juice, but water with food coloring in it. So the fact that we just spent 30 minutes talking about your ideas and writing them down and making them public should tell you that no matter what the outcome of this experiment is, your ideas are the most important thing in this room. So what we're going to do now is we're going to try to give you some more information so that you can revise your ideas if you need to. But we're still talking about your ideas. In your bin, you have a jelly jar that's filled with water that has food coloring in it. So they're all red. It's got a little dish underneath to catch any of this extra liquid that forms on the outside. This is pretty much exactly like the drink that Casey had because it's mostly liquid but there's some ice floating in it. Okay, the only difference is we've sealed the top. So nothing can come out of this jar. Out of the top. Right. So nothing can evaporate out of the jar. So if this side is, if their arguments are correct, what color would we expect the water to be at the bottom of the dish after it's come off of the jar?
Red.
Clear.
So why would we expect it to be red, Alana?
Because it's coming from the inside of the cup.
So the water inside the jar is red. So if the water is coming from inside of the cup, then it must also come from inside of the jar, and it will be red. So if it's not coming from the inside of the jar, then what do we expect it to be? Clear, right? Is this water on the outside that I feel as it feels wet? Is that coming from inside the jar?
Inside the jar.
How do you know that?
Because you said if it comes from the inside of the jar.
Don't do it. Say that out loud.
So you guys were saying
So how can you explain that it's not red if it's coming from the inside and the water inside is red?
Because the water on the outside is clear.
Exactly. It's coming from the outside.
No, it's coming from the inside. Look at it.
So
it's not red.
It's coming from the
It's clear. It can't come from the inside unless it be red.
But it's cold. And then
It's cold on the outside.
The coldness makes it like
from the inside, but the ice is melting. So it makes it white from the outside.
okay.
Because when the ice melts, it'll like make the water like different. Like if it's with food coloring, and the ice will like melt, and from the outside it'll be a different color.
What do you mean?
Like if that ice melts, I think that's what I'm. If
that it's melting, so that's why the color is that clear.
So are you suggesting that this ice, when it melts, gets collected down there?
Yeah.
So how is it getting there?
But there's no hole or anything at the bottom. And even if it was like collecting it.
Do you remember the experiment you're talking about? What we did? Can you explain what we did in that experiment?
We heated it up. The side was soda in there, and it was a solid. And then it's heated up. It started to melt it, and then it turned into hot water, hot liquid, and then the air of it was passing onto the other side and making the air turn to water.
This question one more time, but this time I would like you to include the jar in front of you as evidence. So you should have these words. Maybe the word red and the word, actually you could probably even just use the word red.
If the one on the inside is actually the outside, the one on the outside is
Daniel, did you put my notes there yet?
Yeah, I did.
Okay.
So I want you to look at this question. Whoa, what a shift. We have a huge shift. Look at where all those blue Post-its are. We still have people that disagree. Over here, we've got some ideas. This person summed it up really well. The water came from outside because the jar had clear water outside it. It wasn't red. Okay. He just said, well, the warm air is heating the glass molecules and making them move apart, so there is space for stuff to move between them. So I want you to think back to the Coke and 7-Up flask. What did we do with that flask that had the soda in it?
Heated it.
We heated it. How much did we heat it? A lot. For almost the whole class period, right?
And it kept popping off in between.
It did keep popping off. Did we ever see the food coloring out of that soda leak out through the glass?
No.
No, we didn't. So, because we're running out of time and I want to actually address this other experiment, we're going to leave this disagreement kind of hanging there. Okay? That's an okay thing to do, is to leave the disagreement as it stands. I'm going to dry off all of the water on the outside of this jar. I'm going to come around the room really quickly so that you have a chance to see this. What we're looking for is any water that's formed on the inside of this jar, because at the beginning there was none. You can try and wipe it away if you want, but I'm going to move really fast. And I'd like you to do the same thing you did with the red jar, but now you're writing about the jar full of air. So you're writing a new Post-it now to answer question 1 and provide evidence for it. So is there water, are there water molecules floating around in the air? And how do you know? I dried it off, yeah. So that, you can't wipe it away, so it's on the inside, right?
Over the course of these lessons, we've seen Anna set up multiple chances for her students to reason out loud. They are reasoning not just about the classroom activities, but about everyday experiences, like containers of water becoming moist on the outside, or windows in a house getting steamy. There are dozens of opportunities to talk, and the teacher carefully structures these so that the talk stays focused, so that it builds upon previous ideas, so that everyone gets to participate in doing and talking science.